standard molar enthalpies of formation. And that sounds complicated, but we're going to use this to basically calculate some enthalpy changes stuff. Delta FH, you've seen that in your data booklet, yeah? That's the heat of formation, right? That's the molar enthalpy, kilojoules per mole. It's in your data booklet, and it's for formation, okay? The change in enthalpy when 1 mole of a compound is formed directly from its elements at SATP, standard ambient temperature and pressure, okay? One of the things you have to know about as far as a reference energy state, it's what it's called, is all elements are given a formation of 0. In other words, to make an element, like to make oxygen, for example, requires no energy. It just naturally occurs, okay? To make nitrogen or carbon, okay? Carbon is found in the, it's an element, okay? It doesn't require any energy to make that, all right? Any of the elements up there all have what we call a reference state of a reference energy state. All elements delta formation H0. All elements have 0. So once again, we don't have to put energy into making an element. They just naturally occur. Okay? When do we put energy into something? Well, if we want to make a compound, for example. If we want to make a compound, we have to put energy into that compound to make those elements come together. Or in some cases, if we take a compound, it might require energy, or in some cases, it might give off energy to get back to its elements. Okay, and of course, that's formation decomposition. And there's values associated with that. There's energy that's required or absorbed in order for that to happen. Okay, but as far as elements go, there's no energy required to make an element. Okay, they're just naturally occurring. Some compounds have more potential energy than original elements. Others have less. Okay, it just depends. An EP diagram of a formation reaction can be used to identify this property. So, for example, the formation of ethene. Okay, to make ethene, right, C2H4. It requires 2 carbons and 2 hydrogens, and of course you would have to put in 52.4 kilojoules of energy to make C2H4 ethene. Okay, so we've done that before. That's a potential energy diagram. This is obviously endothermic. Yes, you have to put energy into it to get your products. All right. In this case here, okay, formation of carbon monoxide. To make carbon monoxide, okay, carbon and half an oxygen gives you carbon monoxide. This one is exothermic, so it obviously gives off energy. So if you take some carbon and a half an oxygen, mix those together, it would actually release energy. There's more energy in the reactants here, potential energy in the reactants, than there is in the products. There's more potential energy in these reactants than there is in the products, whereas vice versa, there's more potential energy in the products in this case than there is in the reactants, right? So at the end, when you're done this reaction, you have now more potential energy to do something with. In this case here, you've lost potential energy. Carbon monoxide has less potential energy than your reactants did, okay? And obviously this would be an example of an exothermic reaction, all right? In general, the less potential energy stored in a chemical, the more stable that chemical is considered to be. Okay, CO is more stable than in its component elements. CO is more stable than its component elements. So let's go back to here for a second. So they're saying that CO is more stable. It has less potential energy. Okay, so carbon monoxide is more stable than this here. Okay, and if we went back to the first one here, the elements, these would be more stable than the products would be. Okay, so make sure you guys know that. Make sure you guys understand that. Okay, and basically, like I said, C2H2 ethene is less stable than its component elements, is what it should say there. Okay, so we do need to talk about a little bit about thermal stability, and I'll tell you the easiest way to do this. Okay, when we talk about thermal stability, there will be questions based on this. In other words, how stable is this compound, kind of thing. Thermal stability is a compound's ability to resist decomposition. So think about that. It's the ability to resist decomposition. So if I were you, and they give you these types of questions here, anything to do with thermal stability, the thermal stability depends on decomposition. So the first thing I would do is make sure you understand that it's for decomposition. If you have a formation, you might want to flip it for decomp. You have to make sure we're talking about the right thing here, so decomp. The more endothermic a compound's decomposition reaction is, the greater its thermal stability. Now, I'm missing something here, didn't I? You guys have a chart there, don't you? Yeah. Let me just, maybe it's on the next page. No. Okay. Let's see here. Which color is going to show best? So you guys, yeah. So you have right here, guys, CH4, which is a positive 74.6, and you have C3H8, which is a positive 103.8. Okay. When you look at these, okay, also, by the way, yeah, and this tells you here that this is delta H, and this is the important part for simple decomposition here, okay? So that's the important part. And now let's we'll get you to get your data booklets out too, and we'll kind of go through just maybe another quick example here. But when you look at these two, okay, which one is going to resist, and this is really the question when they ask about thermal stability, which one resists breaking down more? Which one is more resistant to breaking down? And it's C3H8, right? Propane. Why? Because if you compare potential energy diagrams, if you want to do that, that's fine, okay? Look, the reactants start here, right? You have to put in 74.6 to get to CH4, okay? In other words, you would have to, you'd have to start with CH4 here. If you wanted to break down CH4 into carbon and hydrogen here, you would have to put in 74.6 kilojoules of energy, okay? All right. If you wanted to break down propane, you would have to put into 103.8 to break down propane into carbon and hydrogen. Now, I didn't balance those, but okay. Which one resists breaking down more? Well, which one do you have to put more energy in to break it down, right? If you start with CH4, okay, I basically have to put in, okay, so I start at CH4, and I start adding heat, and I start adding heat, and I get to 25 kilojoules, I get to 50 kilojoules. And once I get to 74.6, it now breaks apart into carbons and hydrogens. I've broken it down. I've taken CH4 and broken it down into carbons and hydrogens. I've decomposed it, okay? If you start with propane, you get to 25 kilojoules, you get to 50, you get to 75, you get to 100, it's still stuck together, yes? I get to 103.8, it finally now breaks apart, okay? So decomposition, for decomposition, right, the bigger the number, the bigger the positive endothermic reaction is, the more stable it is, because that means you have to put in more heat to break it down, okay? Yes? Okay? Let's look at your data booklets here. Let's pick out two of those, okay? Real quick here. There's always questions on thermal stability, guaranteed, okay? So look at your, look at this page here, your formation, your heats of formation here, guys. And let's just even look at, for example, methanoic acid. Let's find that one. I just picked this one. And let's look at methanol. Okay. Which one is more thermally stable? Which one's more thermally stable? Think about that for a second. Look at those two. And I just picked them because they're right next to each other. So once you find one, you'll find the other one. Which one is more thermally stable? And remember, they might even tell you this, for example. This is a what? Negative 239.2, and this is a negative 425. 425, right? But remember, when we're talking about thermally stable, we're talking about the ability to decompose it. This is for formation. So the first thing you should absolutely do is change these to positive 425, right? And positive 239. Yes? Because we're talking about decomposition here. How much energy is required to break it into elements? Break that compound apart, right? We're not trying to make it, we're trying to break it apart. So out of these two here, right? So remember, in your data booklet, it's for formation. So if you want decomp, you flip it, right? So we're really comparing these two numbers here. So which one's more thermally stable? Which one requires more energy to put into that endothermic now, right? Which one requires more energy to break that compound apart? And of course the answer is methanoic acid, right? Takes almost twice the amount of energy that you have to put in to break down methanoic acid. Okay? So this one would be more thermally stable. Okay? So please be aware of that. All right? There's always, like I said, there's always good questions on that. Is that good? Any questions, guys? Okay? Like I said, make sure you're comparing decomposition stuff. That's what you need to do there. All right? Now, next, we're going to talk a little bit more about Hess's Law. Now, Hess's Law, you might say, we've done Hess's Law already. I need to fix this here. Let's see, can I fix this? Where's my little... Well, there we go. You might say, we've already done Hess's Law stuff, and we have. I've given you some equations, and you guys have rearranged them, canceled stuff out, got the delta H stuff, right? So what happens, though, what if we need to be able to find, for any equation, what if I don't give you those three given equations to manipulate and turn around and flip signs and multiply by 2 and divide by 3 and all that other stuff? What if there's no equations? Well, that's something that you guys need to be able to do, okay? So after today, well, I don't know if we'll get done today here, but after this lesson here, basically, you will have every tool that you need to figure out any equation that you have to for delta H, okay? So we're not going to tell you delta H anymore. You're going to figure it out on your own after this, okay, for any equation that we give you, all right? So usually in the questions, we've been giving you delta H for all these reactions, right? We're not doing that anymore, okay? You're going to do that. Hess's Law says basically it's the sum, okay? This is the fancy thing for sum here. Sum of the products minus the sum of the reactants, okay? And that will give you delta H, all right? You have to think in terms of what are my products and what did I start with? Well, if it takes so much energy to form this particular product and this particular product, and if it takes so much energy to make the reactants, if I subtract the products minus the reactants, I should be able to figure out the total enthalpy change of that equation. And this is kind of what it looks like here. Now, this looks a little complicated here. You notice we also have N. You'll notice we have delta FH. So probably a big deal in this one here would be this booklet here, delta FH. These are all the values for all the compounds that we're going to give you here. N times the heat of formation for any of the products, and N, the number of moles, times the heat of formation for the reactants. If we subtract those two, that'll tell us the enthalpy change for that equation. This equation can be used to calculate the enthalpy change in kilojoules for any balanced chemical equation. So let's take a look here. I really need to get rid of this background here. So if we want to determine the enthalpy change for the combustion of methane, here's what we're going to do. That's what you guys have next, right? Just to make sure I'm not skipping anything. So I want to find the enthalpy change. You know what? I'm just going to scooch this up here because I don't like that. If I want to find the enthalpy change, and yes, sometimes it's a notation thing, so sometimes you'll see this little 0 up here kind of thing. It basically just means that enthalpy change for this equation. You're going to take the sum, and I just write it like this, guys, of the products minus the sum of the reactants. Okay? So you don't need the whole entire formula. Really, all you need to know is this, okay? It's the products minus the reactants. Products minus reactants. That's all it is, okay? So, I'm going to use big brackets here, okay? Because I'm going to have some multiplying inside of here. So I look at the products. So follow me here. It's actually very, very, very easy, guys. We go back to the balanced chemical equation. It has to be balanced, of course. And I say, okay, what's my products? Here's my product side. If you don't know that, that's not good, okay? Here's my products here. I need 1 carbon dioxide gas. So, data booklets, get them out. Down here, I'm going to take 1 times. And in fact, just for this first one, guys, I'm just going to put the carbon dioxide gas above there, just so you guys have a little reference thing for yourselves. Let's find carbon dioxide gas. What is it here? You'll probably, negative 393.5. So I put that in here, negative 393.5 kilojoules per mole, correct? Because that's what heats of formation are in, yes? Tells you at the top, kilojoules per mole. Okay, I got 1 mole, right? So 1 times, well, in fact, you can even put that in here. That's 1 mole. That's from the balanced chemical equation at the top. 1 mole of carbon dioxide. Plus the sum of the products minus the sum of the reactants. So what else do I have for a product here? Let's see. I have 2 water gases. So I'm going to go down to here and I'm going to say 2 moles of water gas. Okay, so you're going to look up water gas. Now this is where it gets, once again, very important here. Make sure you pick the right one. So it's a negative 241.8 kilojoules per mole. All right, and that is all of my products. Okay. And obviously, if you got 4 products, you'd have to do 4 of those, right? So you sum the products. That's what I've done. I've added those 2 products together. Yes? Follow me so far. This isn't hard. No. Okay? Minus the sum of the reactants. Okay? So once again, I'm going to put some big brackets here. The reactants. Okay? And of course, this is going to give us delta H, by the way. All right. So what are the reactants? Well, let's take a look. How much energy does it take to make CH4? Well, let's find out here. CH4 is methane. And once again, if you don't know that, well, it tells you in the question, but you'll have to obviously find that there. It's a negative 74.6. And I have 1 mole of it, right? So 1 mole of negative 74.6 kilojoules per mole. Okay, and by the way, this was your methane here. All right, let's go back up to the top. We got 2 moles of oxygen. So I'm going to say plus 2 moles, and this would be your oxygen gas here. How much energy does it require to make oxygen? Look in your data booklet if you want. How much is it? 0, right? We talked about that earlier. To make elements, right, they naturally occur. We don't have to put any energy in to make elements. They naturally occur. So this is actually 0 kilojoules per mole. Now, you're going to ask me, do I have to put that in, coach? No. Okay? It's okay. But I'm going to put it in there for now just so you guys get the first example kind of under your belt here. All right? So that's all. That's all you need to do. So if you're looking for delta H, you're going to take the sum of the products minus the sum of the reactants. Okay? We're going to type this into a calculator. Now, the only thing that could possibly go wrong is your calculator might give you the wrong answer because it's a calculator. And you know, it's never your fault. So it's got to be the calculator. Maybe you guys don't have a good calculator. Get one. You just type it in like you see it, guys. So 1 times negative 393.5. And we're going to add on there 2 times negative 241.8. Okay? Now, this is where you got to be a little bit careful. Okay? If you're going to do this properly, all right, we're going to go, obviously, now it's up to you. You might want to just get an answer for this and then go minus and then put big brackets around the next part. The important thing here, guys, is, and you should do this on your calculator right now, by the way, instead of me just doing this for you. You should be doing this because you need to make sure you get the right answer here and make sure you got the right system down. Because there is a potential that you could royally mess this up even though you know what you're doing here. So it's this minus all of this, all right? So to get the right answer here, you want to subtract all of this in brackets here if you're going to do it all in one step, okay? And even if you hit enter right now, after the products part, there's still a chance you could screw this up. Because if you don't put big brackets around here, you're going to go this minus this plus this. And that's not the case. It's this minus all of this. And the answer you should get for this, by the way, is negative 951.7. Yes? Okay. All right. So double check it. Make sure. Is that right? Somebody else get that? Who else got that? No one else got that. Oh, sorry. I see my problem here. Oh, sorry. See, it's the calculator's fault. That's what happens. Sorry, my bad. Oh, no, that's right. Plus 2 times... I think I saw my mistake here. Minus... Oh, sorry. Minus a negative 74.6 here. And you have to be careful with this minus thing here, right? So, sorry. Yeah, you're right. Oops. 802... Oh. There we go. 802.5 is what we should have, yes? Better? Okay. See? Calculators, they're not reliable at all. Okay? So, make sure it's this. Make sure you have the minus all of this, of course. All right? So it should work out. Is that right now? Negative 802.5? Yeah. Okay. Yeah, sorry. I see what I did wrong there. All right? So, like I said, just be careful with that. But that's all you really need to do is products minus reactants. And now guess what? Now, you should know the molar enthalpy of methane, right? Because, look, next thing I'm going to get you to do is say, okay, well, you said CH4 plus, how many oxygens? Was it 2 oxygens? This was a gas too, I think, right? And that gives you CO2 gas and water, of course, gas. What was the carbon dioxide again here? 1 and 2, right? Okay. And over here, you'd put delta H equals negative 802.5 kilojoules, right? You've just found that last delta H thing. You can do that now. You have the power. You have the power, right? Hallelujah. Now, you can do, hey, delta CH, right? For methane, for example, the molar enthalpy of methane combustion, negative 802 per 1 mole. There's your molar enthalpy now, okay? So there's lots of stuff you can do now. All right, photosynthesis, what is it? 6 carbon dioxides and what?
6 waters.
And 6 waters. Gas? Liquid. And that gives you what? C6H12O6. And that's a solid, isn't it? And, of course, 6 oxygens. Okay? So there you go. Like I said, obviously make sure, okay, and it's getting that time now, we got to start looking back at some of this stuff here. Where, by the way, where does, if there's a question on energy, where does it come from? Sun. Always the sun. Yeah. Always. Okay. So, anyway, this one here. Okay. What's the enthalpy change associated with that? You can do that now, right? We should be able to figure this out. So let's figure it out. Delta H. Maybe I won't screw this one up. Who knows? Remember, products minus reactants. It's never a bad thing to write this down, guys. And that's all I do. I'm not going to get too crazy with formula kind of thing. It's the products minus the reactants. Okay? So we got 1 mole. And in fact, 1 mole times C6H12O6. So you're going to have to look that up, of course. What is that here? Where is it here? Glucose. Negative 1273.3 kilojoules per mole. And we're going to add on to that 6 oxygens. Well, once again, you might say, do I have to really put this in here? No, you don't. Okay. However, I'm going to. Okay. So the products, one mole of glucose, right? 6 moles of oxygen. Oxygen's an element, so 0. Subtract from that the reactants here, 6 times carbon dioxide, which once again is negative 393.5. That's one you're going to have to probably do over and over again here. A lot of carbon dioxides. And, of course, 6 water liquids. That's different. Okay? So, 6 water liquids. 6 water liquids here, let's see, negative 285.8, according to your data booklet. Okay? And let's just simply add these up, and hopefully I'll get the right answer this time. All right? So, that's all you need to do. Let's see here. 1 times negative 1273.3, subtract 6 times 0, of course, which is 0. 6 times negative 393.5, and 6 times a negative 285.8. Should be good. I got 2802.5 kilojoules. Yes? Somebody else? Double check? Okay. All right. Yeah, I got one right. Okay, 1 out of 2, that ain't bad. It's a song about that. So, positive 2802.5 kilojoules. Makes sense, I hope, right? Photosynthesis, you need energy, right? So you need to put energy in, apparently 2,802.5 kilojoules. So, once again, you could write out the equation, put the delta H at the end, or you could write out the equation, put the delta H term within the equation, etc., etc. Okay? I know we're running out of time here, guys, but let's get you guys to take, you know what, I'll get you guys to do this one for homework, maybe for me, okay? I told you this before, but remember, I told you there's a big difference between water gas and water liquid, right? Why? Because remember, in a bomb calorimeter, okay, the water is in liquid state in a bomb calorimeter. So, when you go to do this one here, guys, okay, you're going to write out a combustion equation for this, right? Combustion for ethane when burned in a bomb calorimeter. So make sure that water is a liquid as part of the product there, okay? And we'll do that, just that example for homework, all right? And then tomorrow I'll give you some time. We'll probably do a quiz again tomorrow, and probably a little bit of Hess's Law from the other day there, just manipulating one question or something. And we'll give you some time to work on these questions tomorrow, okay?